This is the 8th lecture on the waves topic. In this lecture we're going to be looking at standing waves in air columns and on rods and membranes, and we're going to be looking at beats. This is the last lecture where we'll be covering new material. This lecture covers textbook sections 17.5 and 17.6. First of all, a quick recap of the most important ideas from last lecture. We saw sound levels were defined by beta and they're measured in decibels. They're given by 10 log to the base 10 I on I naught, where I naught is the reference intensity, the lowest intensity of sound that we can hear at 1000 Hertz. We also saw the Doppler effect. We have the velocity of sound, the velocity of a source, and the velocity of an observer. And the frequency observed by the observer is related to the frequency emitted by the source through V plus V naught over V minus Vs. This is for the case when the source and the observer are moving towards each other. If one is moving away from the other, then we need to switch the sign in front of that term. And we also saw shock waves happen when a source starts moving faster than the velocity of sound or the velocity of the waves in that medium. In that case, the source overtakes the sound waves that it emits, and we get a shock wave like this generated. Sine theta of this angle here is given by V over Vs, and Vs on V, the velocity of the source divided by the velocity of the wave, is equal to the Mach number. On to new material, standing waves in air columns. So these work in much the same way as standing waves on a string. We just add the original wave and the reflection. For a standing wave, a closed end must be a displacement node. So if we have a displacement node here, we have a maximum pressure as well. It's a pressure antinode. So that's because the particles here can't vibrate in and out, because there's an end there stopping them vibrating. If a pipe is open at both ends, then both ends are antinodes. So we have pressure nodes here and displacement antinodes. Now, it's not obvious in an open pipe that reflection will occur, and so you actually get a standing wave. But when this wave moves out of the pipe, it's like moving into a different medium because it's no longer confined around here. And so when the wave moves from one medium to another, some of it is reflected. So for that reason, some of the sound is reflected, and we do get a standing wave in a pipe open at both ends. In a closed pipe, the first harmonic, or the fundamental frequency, occurs when we've got a quarter of a wavelength in the pipe. So we've got an antinode here and a node here, so that's quarter of a wavelength. So in this case, lambda over 4 is L, or lambda is equal to 4L. And so the frequency of this first harmonic is given by F is equal to V on lambda, which is V over 4L. So that is our fundamental frequency, F1. Now, we call the next harmonic the third harmonic, and it's when we have 3/4 of a wavelength in the pipe, in which case L is equal to 3/4 of a wavelength, and so the frequency of our third harmonic, F3, is equal to 3 times the frequency of the first harmonic. And for the fifth harmonic, we have 5/4 wavelengths in the pipe, and the frequency of that harmonic is 5 times the frequency of the first harmonic. For a pipe open at both ends, the first harmonic occurs when we have half a wavelength. The shortest distance between two antinodes is half a wavelength. So in that case, the wavelength is equal to 2 times the length of the pipe. And the frequency of the fundamental in this case, or the first harmonic, is V over 2L. The second harmonic occurs when the length of the pipe is equal to 1 wavelength, and so we have 2 times that fundamental frequency. And the third harmonic occurs when we have 3 half wavelengths in the pipe, and so the frequency in that case is equal to 3 times the fundamental frequency. So here's a question. What will happen to the frequency of notes produced by a flute, an air column, as the temperature increases? And what will happen to the frequency of notes produced by a violin, a string, as the temperature increases? In the flute, or the air column, which is a very simplified flute, we have a wavelength something like this. So in this case, the wavelength is set by, so it's proportional to the length of the pipe. Now, as the temperature goes up, the length of the pipe will change a little bit, so we will have the change in length is equal to the length times alpha times delta T, but these alphas are generally of order 10 to the minus 6, so this thing is a very small change. And so the wavelength is really not changing very much. It's got a very small increase. Now, the velocity of sound, velocity is equal to the initial velocity over the new temperature over the initial temperature. So the velocity does increase as the temperature increases. So we have V is equal to F lambda. This is increasing just a little bit, and so this tells us that the frequency must increase as the temperature increases. Now, on a violin string, we have that the length of the violin string does change due to the same reason here. The change in length is equal to length alpha delta T. So in this case, this is actually a more significant change compared to the other things. The velocity of the wave on the string is given by the square root of the tension over the mass per unit length. Now, we're not changing the tension, that's fixed on the violin by the little pegs at the end. Mu, the mass per unit length, is going to decrease a little bit as the length is decreasing, but this has got the square root here. So as this decreases, the velocity will increase just a little bit, but this length tells us how the wavelength increases, because the length is equal to lambda over 2. So the wavelength increases a lot compared to the change in the velocity. So V is equal to F lambda, and if the wavelength is increasing a lot and the velocity is only increasing a little bit, then the frequency must decrease as the temperature increases. So just a note about how some instruments work. Air column instruments resonate at their natural frequency. Generally, a wide range of frequencies is put into the instrument by the reeds, lips, etc., and only certain frequencies cause the instrument to resonate, the harmonic frequencies. So these are the ones that we hear. So even though we're putting in a whole range of frequencies, we only hear the resonant ones.
Another thing that we need to take into account is end effects. End effects effectively lengthen the pipe, so the wavelength extends out a bit from the end of the pipe. The end effects can be taken into account by using two harmonics to calculate the required value. So in a minute we'll do an example showing how to do that. So do end effects make the natural frequencies higher or lower? Well, end effects are going to make the wavelength longer, and as the velocity is staying the same and the wavelength's getting longer, larger, the frequency is going to end up smaller, and so we'll have a higher frequency. So a formula for taking into account end effects is that the actual length of the pipe, that's the actual length of this black line here, is equal to n lambda over 2, so the number of half wavelengths. In this diagram we've got 1 half wavelength, minus 2 times the end effects. Now, this 2 is unimportant. We can either consider the end effects as one entity or as two things which occur at both ends. So here's a question for us to practice using end effects with. You're provided with a large measuring cylinder that can be filled with water, a meter ruler and a tuning fork with a known frequency f. Describe how you could measure the speed of sound. Make sure that you account for end effects. So in order to do this, we should start with our measuring cylinder and hold the tuning fork with known frequency f over the top of the measuring cylinder. We should fill the measuring cylinder up with water and then slowly empty it until we hear the first resonance. Now, with the meter ruler, we can measure this length L1, the length from the top of the water to the top of the measuring cylinder. Now we've got some end effects up here. So we know that L1 plus the end effects is equal to quarter of a wavelength. What we should then do is empty some of the water out until we hear the next resonance. So that will occur at some height like this. So we've got this standing wave here. So in this case, we can measure this length here. Well, let's call this L2, and then we've got end effects up here. So L2 plus end effects, you can see this is 3/4 of a wavelength. So let's call this equation 1 and equation 2. And what we're trying to do is find the velocity. We know the frequency from the tuning fork, and so if we can work out the wavelength, we can then use V equals F lambda to get the velocity. So let's do equation 2 minus equation 1. So we'll have L2 plus end effects minus L1 plus end effects. So the end effects cancel out, and we have L2 minus L1 is equal to 3/4 lambda minus lambda on 4, so this is equal to lambda over 2. So this tells us that lambda is equal to 2 L2 minus L1, and so to get the velocity, V is equal to 2F L2 minus L1. And we've accounted for end effects there, and so this would be a way to calculate the velocity of sound.
Okay, a quick quiz. A pipe that is open at both ends resonates at a fundamental frequency F open. When one end is covered and the pipe is again made to resonate, the fundamental frequency is now F closed. Which of the following expressions describes how these two resonant frequencies compare? A, F closed is equal to F open. B, F closed is equal to a half F open. C, F closed is equal to 2F open. Or D, F closed is equal to 3/2 F open. The fundamental in the closed pipe looks like this. So if our pipe has length L, we have lambda is equal, for the closed pipe, is equal to 4L. For the open pipe, once again with length L, our fundamental looks like this. So we've got half a wavelength, where here we had a quarter. So the wavelength for the open pipe is equal to 2L. So we can see that the wavelength for the closed pipe is 2 times the wavelength for the open pipe. Now we have the equation V is equal to F lambda. V is the speed of sound in air, and so that's not changing, that's constant for these two situations. So this tells us that F open, lambda open, is equal to F closed, lambda closed. And so F closed is equal to F open, lambda open, over lambda closed, which is 2 lambda open. So this is equal to a half F open. So the frequency in the closed pipe is a half the frequency in the open pipe. And so the correct answer here is B. Okay, you should try homework set 6 for 1121 questions 10 and 15, for 1131 questions 13 and 18. Okay, now we can also get standing waves on rods. If we clamp a rod at a certain place, then that forces us to have a node at a place. So if you get questions like this, really you just have to draw a diagram showing where the nodes and antinodes are, and so that you can work out what the wavelength of your standing wave is. So wherever it's clamped, we'll have a node. If we clamp it a quarter of a way along, then we have a node a quarter of a way along, and so this is our fundamental frequency for this rod here. Now strings, if you pluck a string, wherever you pluck it, you're creating an antinode. So to answer questions where you're plucking a string a fraction of the way along, draw a diagram, show the antinode at the place you're plucking it, and use that diagram to work out the wavelength. We can also get standing waves on membranes. This video shows we've got a frequency, a sound input, and you can see the sand moving around the surface to mark out the standing wave pattern that is generated. So membranes can also have standing waves set up on them, as shown in this video. The sound is not harmonic, as the frequencies that will set up standing waves are not related by integers. So instruments like drums produce what we interpret as noise rather than music, as the frequencies, the fundamental frequencies that they generate, don't have this nice harmonic sequence. They're not related by integers. Okay, and the final concept for the course, beats. Standing waves occur due to spatial interference. So this is our equation for the standing wave. Y of xt is equal to 2a sine kx cos omega t. We add the waves with the same frequency at each x to investigate the interference pattern. Now, imagine choosing a point in space and adding two waves with slightly different frequencies. You'll get an interference pattern through time. This is called temporal interference. So for our travelling wave, we've chosen a point in space. So we've replaced kx plus phi with pi on 2. That can be anything because we can choose phi randomly to make this so. So this is wave 1, this is wave 2. The only difference between them is slightly different omegas, which is slightly different frequencies. So a sine pi on 2 minus omega 1t, we can write this as a cos 2 pi f1t, and here we have a cos 2 pi f2t. So the only reason we've put this pi on 2 here is so that we can make them into cos functions so that they're nice and easy to add. Okay, so y1 plus y2 is equal to a, pulling the amplitude out the front as a common factor, cos 2 pi f1t plus cos 2 pi f2t. So using our rules for adding cos functions, this becomes cos and then the sum of these things and then times cos minus the difference of these two things. So we end up with 2a cos 2 pi f1 plus f2t times cos 2 pi f1 minus f2t on 2. Now this is a big number, so as t changes, this cos function here oscillates between 1 and minus 1 relatively rapidly. f1 minus f2 on the other hand, for beats we choose to be a relatively small number. We choose f1 and f2 as very similar. So here, so this part of the cos function is oscillating very slowly between 1 and minus 1. So as we superimpose these functions, what we end up getting is here's the slow oscillation here due to that f1 minus f2, and here's the rapid oscillation due to the f1 plus f2. So this envelope, the dotted line here, is described by 2a cos 2 pi f1 minus f2t on 2. So that's given by this part and this part of this function. This here is the rapid oscillation between 1 and minus 1. And so the period for this envelope function, that's the time from here to here to here, is given by 2 over f1 minus f2. That's just the inverse of this part of the function here, as we've got the 2 pi there. So that's telling us how long it takes to cover 2 pi. Now what we actually hear if we're listening is we hear this maximum, we hear this minimum, we hear this maximum, we hear this minimum. So over that period we actually hear 2 beats. We hear 2 maximums and at the ends the 2 minimums. So the beat frequency that we hear is equal to f1 minus f2, the difference in the 2 frequencies. So beating is the periodic variation in amplitude of a given point due to the superposition of 2 waves having slightly different frequencies. The beat frequency is given by the difference in these frequencies. We've got the absolute value signs because it really doesn't matter which one we label as f1 and which one we label as f2. So to practice using this, try homework set 6 for Phys 1121 question 11 and for Phys 1131 question 14. Okay, and finally some questions to do. 2 identical piano strings of length 0.750 meters are each tuned to exactly 440 hertz. The tension in one of the strings is then increased by 1%. If they are now struck, what is the beat frequency between the fundamentals of the 2 strings? Okay, so we're told that the frequency initially is 440 hertz, and we're asked what's the beat frequency when we change the tension by 1%. So we're told that the length of the string is equal to 0.750 meters. Okay, now as this is a string, we're considering the fundamental, the wavelength is equal to 2 times the length. This is half a wavelength here. Here's L. And so this is 2 times 0.750, which is equal to 1.50 meters. Now what we need to do is work out how is the frequency going to change when we change the tension. We've got the frequency in the string which doesn't change, but in the one that does change, we have frequency is equal to velocity over the wavelength. We know the wavelength, we've calculated that because we're not changing the length of the string. So what you need to look at is the velocity. For waves in the string, the velocity is equal to the square root of tension over the mass per unit length. And the mass per unit length is not going to change perceptibly. So V1 over V2 is equal to the square root of T1 over the square root of T2, as this part is constant. We're also not changing this wavelength, so we can actually say that V1 over V2 is F1 over F2. Okay, now T1, that was our original function, tension T1, and then T2 is increased by 1%, which tells us that T2 is equal to 1.01 times T1. So we can put this over the square root of 1.01 T1. Okay, so these square roots of T1s cancel out, and we have F1 over F2 is equal to 1 over the square root of 1.01. So F2 is equal to square root of 1.01 F1, which is equal to 442.19 Hertz. So the beat frequency, F beat, is equal to the absolute value of F1 minus F2, which is 442.19 minus the 440. So that gives us the 2 Hertz, 2.19 Hertz. Okay, next question. Water is pumped into a tall vertical cylinder at a volume flow rate R. The radius of the cylinder is little r, and at the open top of the cylinder, a tuning fork is vibrating with frequency F. As the water rises, what time interval elapses between the successive resonances? Okay, so in this question, we have a cylinder, we have water flowing in at a rate R, we have a tuning fork with frequency, say, F, and this cylinder has radius little r. Now the rate of flow of water is equal to the change in volume with time. For our cylinder, it's got surface area pi r squared, and then the height is also going to change, so this will be times the change in height with time. The radius is not changing with time, so this is the part which is changing with time. And now the change in height between resonances, well, we have resonances like this at a quarter of a wavelength, and then at 3/4 of a wavelength, and then at 5/4 of a wavelength. But the difference between each of these resonances is equal to lambda over 2. So what we need to do is just replace delta H with lambda over 2. So what we have is R is equal to pi little r squared lambda over 2t. And what we're asked for is the time between these resonances. So just rearranging this, we get the time between them is equal to pi r squared lambda over 2r. However, we don't know lambda, we do know the frequency and the velocity. So V is equal to F lambda, tells us that lambda is equal to V on F. So the time between these resonances is pi r squared over 2r times V over F. An aluminium rod is clamped 1/4 of the way along its length and set into longitudinal vibrations by a variable frequency driving source. The lowest frequency that produces resonance is 4,400 Hz. The speed of sound in an aluminium rod is 5,100 meters per second. Determine the length of the rod. Okay, so here's our rod. We've clamped it 1/4 of a way along, so we force that to be a node there. So we can have an antinode here, and our wave will look like that. So 2 nodes, antinodes, this means that the length of the rod is equal to the wavelength for fundamental frequency. So now what we need to do is work out the wavelength. The wavelength is equal to the velocity of the frequency. We're told that the velocity is 5,100 and we're told that the frequency is 4,400. And so solving this on the calculator we get 1.159, which to three significant figures is 1.16 meters. And so that is our wavelength, which is our length of the rod. Okay, another question. A section of drainage culvert 1.23 meters in length makes a howling noise when the wind blows across its open ends. Determine the frequencies of the first three harmonics in the culvert if it is cylindrical in shape and open at both ends. Take V is equal to 343 meters per second as the speed of sound in air. And then B, what are the three lowest natural frequencies if the culvert is blocked at one end? Okay, so for the first one, we have the pipe like this. It's open at both ends. V is equal to 343 and the length is equal to 1.23 meters. So we have the wavelength is equal to 2 times 1.23 meters, as we've got half a wavelength in here. So the frequency is equal to V over lambda, which is equal to 343 over 2 times 1.23. Solving that on the calculator, we end up with 139 hertz. For the second case, we have a full wavelength in there, so wavelength is equal to 1.23, so the frequency is equal to, so actually we don't have this 2 here now, so our answer is double this, it's 2 times 139. Keeping all the significant figures from this one, we end up with 279 hertz. And then for the third case, we actually end up with 3.5 wavelengths in there, so it's 3 times this fundamental frequency, so F is equal to 3 times 139 with all its significant figures. That gives us 418 hertz. Okay, so that's part A. For part B, we're told it's now blocked at one end, so the first fundamental frequency will be where we've got a quarter of a wavelength in there, so lambda will be equal to 4 times 1.23 meters, and so the frequency will be 343 over 4 times 1.23, so it'll actually be half of this one, and so that is equal to 69.7 hertz. Now the next frequency will occur when we've got 3/4 of a wavelength in there, so we'll end up with 3 times this. So F will be equal to 3 times 69.7, which will give us 209 hertz. And then finally, the third sound we'll hear will be when we have 5/4 of a wavelength, so F will be 5 times 69.7, so that will be 349 hertz. Okay, another question. A vertical pipe open at both ends is partially submerged in water and a tuning fork vibrating at an unknown frequency is placed at the top of the pipe. The length L of the air column can be adjusted by moving the pipe vertically. For a certain pipe, the smallest value of L for which the peak occurs in this sound intensity is 9 centimeters. A, what is the frequency of the tuning fork? And B, what are the values of L for the next two resonant conditions? Okay, so first of all, we were asked what is the frequency, and we were told that this case was when we had L was equal to 9.00 centimeters. Now, if possible, we would try and take into account end effects, but we have not been provided with enough information in this question as we're only told the length of the first harmonic. If we were told the length of other harmonics, then we would need to consider end effects. Okay, so L is, in this case, is equal to lambda over 4. This is quarter of a wavelength, so our wavelength is equal to 4 times 9, which is 36.0 centimeters. And so our frequency is equal to V over lambda, which is 343 over 0.360. Solving that on the calculator, you end up with 953 hertz. Part B then asked at what lengths will the next frequencies be heard. Well, they'll be heard when we've got 3/4 of a wavelength. So that's 3 times 1/4, which is 3 times 9. So that gives us 27.0 centimeters. And then the next one will be when we've got 5/4 of a wavelength, so 5 times 9, which gives us 45.0 centimeters.